Hello, my name is Alejandra Crespo. I study electrical mechanical engineering. My topic is about what is ray tracing and how is enabling real-time 3D graphics. We have definition is what is ray tracing? Ray tracing is a lighting technique for 3D graphics that mimics this real-world approach. And while it produces the most realistic results, the process has traditionally been too complex for computers to create 3D graphics in real time. Is widely used today for creating ultra-realistic renders for a person and movies, but in this case it can take hours to generate each frame, even on date. Massively powerful computer service ray tracing is a buzzword that generating hot amounts of fiction of hype depending on your point of view. As the way forward for real-time graphics in this light, the next is about in every game the world is made of objects, which when combined consists of millions of triangles. The most basic function of ray tracing is sending of a ray following its path through the 3D world to locate the first object. It reads to determine how it should be lit, texting even a single ray with every object it sent to see if they intersect in two power inefficient and complementary, expecting to be practical in real time. You see, this bunny is divided into boxes using an assured structure. To use ray tracing well, therefore, you need to solve this problem. Is Ricken Dre problem. This can be done by building a ray tracing acceleration. To do this, we can draw the box around our game world, which we then suck debris into the smaller boxes and fill boxes into the smaller boxes until ultimately we have a smaller box contain a minimal number of triangles. We call this descent urgent structure, and it helps us reduce the problem to something current graphics processors can handle efficiently. Is a video I see view ray tracing interactive 3D graphics.
So far we've examined what are called local illumination models, where an object is affected by a light and the result is sent to the eye. Light comes only from, well, light sources. No light is reflected from other objects. There are many more light paths that can be tracked. One rendering technique that can simulate these is called ray tracing. We've seen how the GPU sends each object triangle in turn to their screen and rasterizes it. Ray tracing instead fires rays from the eye through each pixel. Objects are tested against each ray. The closest object found along ray's path is the one that's used to compute the ray's color contribution. You can think of each ray from the eye as rendering a single 1x1 pixel. One way to find the closest object for this pixel is to send every triangle down the pipeline and attempt to rasterize it, using the Z-buffer to keep track of the closest object. This is perhaps the slowest way ever to perform ray tracing. In reality, researchers and practitioners have spent huge amounts of time creating and tuning algorithms to rapidly find this closest object along the ray. Where rasterization gets some of its speed is from the fact that a single triangle usually covers a bunch of pixels. Various intermediate results can then be shared when processing the triangle. At its simplest, ray tracing can give the same result as rasterization. Each ray from the eye finds the closest object along it. The effect of light on the surface is computed and the result is displayed. However, that's just the starting point for ray tracing. For the light-to-surface paths, we've made one obvious simplification for basic rasterization. Objects don't block other objects. In other words, no shadows are cast. In ray tracing, adding basic shadows is trivial. Shoot a ray from the surface to the light. If there's something in the way, the light is blocked and can be ignored. Since all computations happen in world space, we can avoid many of the precision problems found in rasterization techniques such as shadow mapping. Classical ray tracing also offers us the ability to create true reflections and glass effects. For shiny surfaces, we can spawn a new ray in the reflection direction. Whatever this ray hits is what is reflected in the surface and so can be factored into the ray's final color, its radiance. Let's say our sphere is actually glass. Instead of simple filtering, we can also spawn a refraction ray and see where it hits. When it encounters the other side of the sphere and exits, we spawn yet another refraction ray and a reflection ray. We can continue to spawn rays until we hit some limit.
And now is the currency problem. We need to fetch boxes and triangles from our accelerating structure in memory with each ray triggering a fragment program each time it hits an object. Unfortunately, rays are erratic things and they don't necessarily travel in the same direction. In technical terms, we describe this as uncurrencing, which is a problematic no-current data set is bad for modern GPUs. It's a backlight trying to look up information. In an alphabetical order, but the names are given to an axis and completely random order, Q lots of flicking back, and for taking up precious time and consuming precious energy. Is a video about accelerated lighting in Logitech with NVIDIA Quadro RTX and Autodesk Arnold GPU.
So Arnold is a production path tracer. It's a rendering engine, which means that it is the software that is used to create the final frame for film, animation, TV shows.
Arnold aims at simplifying workflows, reducing the number of parameters that an artist has to tweak before getting a nice image and focus on the artistic process.
So what we're trying to do with Arnold GPU is create a GPU production renderer. And Cinesight was really keen on working with us on that.
We've been hearing about GPU rendering for a very long time, but I didn't really understand what was the scope of the design changes that were made to the graphics background. As we learned more about the architecture, then that's when it started to be really more exciting for us.
After we did some testing in London, that went very well. We decided to do more testing here in Montreal, more in a production environment. We did most of our focusing on lighting and look dev, and really just wanted to see how far we could push the GPU. Most recently, we're working on an Indian film, a Bollywood film, where the main character gets to blast off in a rocket ship. We completed 26 shots in the movie with the CPU render, and once we got the GPU render, we thought, let's see what we can do with this. One of the major things that were challenged was keeping the lighting direction and the continuity of lighting the same through all the shots. Now this is done traditionally here by separate artists in separate Maya scenes. They also get reviewed separately. It's a long process, but I think with this GPU technology, potentially could have all those shots done by one person in one scene. We've loaded up Arnold GPU Beta and basically put every single shot in our sequence on the timeline of Maya. So we think a card like the RTX 6000 would really help speed up that process. We can literally go to any shot at any time, rotate a key light, change the color of a light, maybe change your HDRI, and basically have all of them chronologically so you can get all your lighting direction set. This is a huge step for us. When we heard that Autodesk and NVIDIA wanted us to do some testing on possibly a real-time renderer, we immediately jumped in. This is the holy grail, two very trusted companies that we use widely. So it was a very easy decision and opportunity to see what's coming up on the horizon.
We're really feeling the performance here, and we're really happy about the performance, and we know it's going to become even better. This is just the beginning.
Another video is written providing the real-time ray tracing Sputnik.
Rasterization and ray tracing are two approaches to the main tasks when rendering a 3D image, namely visibility and shading. Rasterization uses approximation of how light behaves to decide how 3D objects will look on screen. This method allows for fast rendering and high frame rates. Ray tracing solves the problem of shading a 3D object, or tracing a ray by modeling complex light interactions. Ray tracing is computationally expensive, resulting in longer render times. Video games normally rely on rasterization to achieve smooth gameplay. Professional 3D renders mostly use ray tracing to achieve photorealistic results. Radeon ProRender now combines the benefits of both approaches by rasterizing basic structures and surfaces before ray tracing is used to compute minute light effects like reflections and shadows. This means that viewers end up getting great image quality combined with superior performance and speed. To learn more, visit gpuopen.com.
Applied in Ecuador application, we have 1. Creating ultra-realistic renders. 2. Generate each frame even on today's massively powerful compute servers. 3. Real-time graphics. And 4. Regain data access and execution efficiency, and that also lower power and bandwidth in our processing. This video about real-time rendering of animated light files. Pros and cons. In pros, it is can trace race and do it efficiently, real-time performance, and rapid advances in AI processing. And cons, we have only one, is reduce the number of rays we need to trace. It's a video about reality versus illusion, what is achievable with real-time ray tracing. And finally, the conclusion. There is no doubt that real-time ray tracing has a bright future, making this undoubtedly an exciting time for anyone interested in the 3D graphics. It is based on real-world physics, and ray tracing offers the highest levels of brilliance. But it also delivers great efficiency versus the hacks and approximation that we have been using up to now. The low power restored graphics, pioneering ray tracing work, and continuing innovation in all neural networks all combine to help take graphics the next level. Well, thanks for your attention and bye.